Physics lab for oscillations. So the main goals of this lab were to compare the predicted motion of a mass attached to a spring to its observed motion. This was done by plotting the energy changes occurring in the system for the predicted motion, so the change in kinetic, total energy. Overall, there were some errors in the experiment with a somewhat accurate X position model when comparing the observed to the computational prediction. So what were the key concepts and formulas involved in this lab? So the first one is Newton's second law. This has been explained a lot in past labs and it continues to be used. A new addition is the energy principle. So this is the change in energy of a system, which is represented by delta E, and it's equal to the work done by the surroundings, added to the exchange of energy between systems and surroundings, that is Q. And from this general formula, we can derive equations for different types of energies. So it depends on the system we're dealing with. The main ones we'll be looking at this experiment today will be the kinetic energy, starts with K, the spring potential energy, which comes with gravitational potential energy, which is down below here. So the next thing is to choose our system. So in this case, we chose our system to be the Earth, the spring, and the mass. So basically, nothing is left to surroundings. Because there are no surroundings, W surroundings will be 0, and the exchange between both of them will also be 0, leading delta E to be 0 as well. So the main thing for using tracker was used from a video of the mass attached to the spring. So we used an offset origin, axis being placed at the center of mass, and we went from frame 5 because that's right when the initial movement started, until the last frame, so around like 100 frames. And the length of an object was used as a point of reference, try to keep it as accurate as possible. So for the computational model, we first had to set our initial conditions. These were obtained from the analysis of tracker footage. So we already knew the mass of the object at 0.402 kilograms, so we had that as ball.m, and we calculated the initial position as well, which we used later to calculate the velocity. So then some equations that we set up include the string ones I was discussing before. That's the L hat thing, basically setting the equation, which we later used to calculate the energies here. So that these are equations we set up to be able to make these predicted calculations. Some other equations are all of the Newton's second law we talked about earlier. So net force, force of the spring, force of gravity, and using that to update the velocity and position. Then the main part of this code was the loop. This is where we iterate through the model that we're given under a specific time constraint using the formulas to keep calculating the net force, and that is how we know the energy changes. So here are the results so to discuss this, so as I said, the X position graph seems to be more accurate than the Y position, so maybe the model for the X position was better. And the Y position computational model likely has errors. So we'll discuss these possible errors in a minute. And there seems to be a similar issue with plotting the changes in energy. So the first possible error could be not accounting for other forces like drag, maybe other energies, thermal energy. Maybe it was a lack of accounting for other factors that could have impacted this experiment. Maybe some technical like human errors, like when using tracker, not placing the object, the point when we do the point mass system directly in the center of the object. Maybe errors in calculating the spring constant, which we'll also look at later, as well as other constants in the computational model. And maybe a problem with the axes, maybe the initial, if the offset origin was set to 0, the original, like, first starting position should have been set to 0, so there might have been a mistake with that as well. So some further questions. So what does it mean? Is the energy principle satisfied? So the energy principle states that it should all equal 0, and technically in this graph, yes. We see that the total, the delta E line is at a constant 0, that orange line. However, there's likely errors in the calculations since not all of the energy should be 0. And then let's do a comparison of estimates. So the average oscillation period was calculated by taking difference in between each valley of the graph. So we calculated this number, this number, this number here, and the difference in time between each divided it by 3. We did that for both graphs. So for the X position oscillation period, it was 1.79 seconds. For Y, 1.43 seconds. And between them, there's a difference of 0.36. So this difference has an impact on the calculations for the spring constant, which we talked about earlier. So this might have caused a problem in the computational model and might be the reason why we see the energy graph being like this when it should not be. So the why could we have made this error in the difference? So it could be caused by errors in like I said, mapping the tracker, or maybe some camera warp, something that might have impeded our ability to really see the changes in position. So thank you for watching my lab, and this is all.